Alright, this problem is projectile packet purple, number 4. So this is a basketball player that shoots a three-pointer with a high arc from a 24 feet away from the basket. If the ball leaves the player's hands at 43.4 feet per second, what's the difference in height between the player's hands and the basket? So this is essentially a ground to height. Even though it's not necessarily starting at the ground, we don't know where that actual height ends up. So we have to make our table of information as usual. So we have our delta x, vx, tx. We're going to have a delta y peak to ground, which is going to be its maximum height. We're going to have the delta y cliff to peak, which is going to be from hands to the top, and then a delta y pf here, which is going to be the peak to where it falls. We have our v initial in the y, our time in the y, gravity, and then the velocity at the peak, which is always 0. So we can fill in the things that we know, which is not that much. We know that total, the time y is going to be up plus down, so we're going to have to find those individually. We don't necessarily know which one's going to be greater because we don't know where the peak is, so there's a lot of work that needs to be done in order to get the answers. So overall, we have our v initial and our angle. So our angle is 78 degrees. But our variables and information in the problem are given to us in the wrong units. So our velocity is given as feet per second, which we don't like. So we need to convert that to meters per second. So there are 3.28 feet just about in every meter. So what we're going to do is take that 43.4, divide it by 3.28, and that will get us our velocity that it leaves the player's hands with in meters per second. So for dimensional analysis purposes, we start with feet on the top, we want to put feet on the bottom. So we end up with a velocity of 13.23 meters per second. So that's going to be the velocity initial overall. Not x, not y, just the total. So that velocity is going to be what we're going to work with when we find our components. Then we have to convert 24 feet. Again, we do not like feet, we want meters. So if we take that 24 and divide it by the 3.28, that's going to get us our value in meters. So the player is standing 7.32 meters away from the basket. So that is going to be the delta x. In this situation, we are trying to reach the basket because that's the plan. We want to make a shot. So the delta x that we use is going to be that one. So as far as the diagram goes, this is not a perfect one because we don't know officially where we are, but we're going to have our ball. It's going to get shot from a certain level. Starts 7.32 meters away from the basket. That velocity and the angle are located right there, and then we end up trying to figure out where do we peak. So do we peak prior to the basket, at the basket, well before? Not sure. So to start the problem solving practice, we will find v initial in the x direction, which is going to be v initial multiplied by the cosine of your angle. So plugging in, we have 13.23 times cosine of 78. And that'll get you the x component of velocity, and as a reminder, that doesn't change because there is no force or acceleration in the x direction. So we get a velocity of 2.75 meters per second. We do the same thing for VOY. We use sine instead of cosine because of the triangle. So 13.23 multiplied by the sine of 78 is going to get us our y component. That one will change, so this is just the initial as it leaves the hands. So that's 12.94 meters per second. So that velocity is directed upward. That's right at the starting point when it leaves the hands of the player. And then again, the x stays the same. So from here, we need to make a choice as to what we have to solve for. So we know the distance of 7.32, so it would make sense to find the time it takes to reach the net, because we know 2 of the 3 things on the x side. So by finding time x, that can help us look for some more information. We also now know that v initial y, so we could find the time up if we so choose. Okay, so the time to the net is going to be our time x in this case, because that's the total linear distance. So we have our delta x, which is vx times tx. So our time is going to be our displacement divided by our velocity. So 7.32 divided by our 2.75. That's going to get us the total time that the ball is in the air. So that's the time it takes to reach the net, or at least the net's displacement from the hands of the person. So that's 2.66 seconds. So that's good to know, because what we can actually do at this point is figure out where the peak is, and that'll tell us how much time it takes for the ball to fall after it peaks. So finding time up is going to be the first way for us to find that information out. We know that it starts with a certain y velocity. At the peak, it's going to go to 0, and then we know gravity and time. So this equation is the best choice. So using this equation is going to let us figure out how much time it would take to reach the peak. We can figure out where the peak is then relative to the basket. So if the time up is shorter, we peak before the basket. If it's exact, we peak at the basket, and if it's greater, we'll peak after the basket. So we're going to get a time up value of 1.32 seconds, which, looking at the time total of 2.66, it's pretty close to half. So what that generally means is that the peak happens right in the middle, so the height that we climb is going to be pretty close to the height that we fall. But we're just going to check to see if that actually matches up. And that's, again, only because half of 2.66 is 1.33. So we're going to find the height of the cliff to peak, which in this case is the player's hands to the highest point. So we'll use the free fall equation. Even though technically we do start with an initial velocity, we know that the time it took to go up was that value, so we can use the symmetry to cancel out that b initial. So that's going to get us our 1/2 times negative 9.81, 1.32 squared. So this tells us that on the way up from hands to peak, we travel 8.55 meters. So this doesn't tell us how high above the ground, it just tells us how high above the starting point. So that's important to pay attention to. Alright, so again, like we discussed previously, time down is going to be time x minus time up, because time up and time down together equal the total. So when we solve for that, we're going to get a time down value that ends up being 1.34 seconds. So that means it's falling longer than it's in the air, which is strange, because when you think about basketball, people are not usually as tall as the rim. Although if they release it from a high enough point, it could be fairly equivalent. So looking at that information, we're going to then find the delta y that it falls. So that's that peak to fall value that we talked about when we set up our table. So again, using free fall from the peak, that's going to be delta y fall is 1/2 gravity times time squared. So 1/2 times negative 9.81 times the time down, which is what we just calculated. That's going to get us how far down we are actually going to fall. When you calculate that value, you get 8.81. Now, we rose 8.55 and then fell 8.81. So already that indicates that our basket height is underneath our release point, which seems strange. So, just to verify, let's draw the diagram. So we have our object, it gets launched, we're going to shoot it up to its peak point, it's going to fall back down. So based on the diagram, that's kind of what it looks like. So we're going to have our peak at the middle-ish. On the right side of the screen, that's that 8.81, and it's going to be the entire vertical distance from the top down to the basket. And then on the left side, we have our 8.55. That's going to be the rising height from our launch to the peak. So it seems like the basket's below hands, but it is more likely that they are equal, and the rounding that we performed earlier is what actually threw off the value. So it ended up changing, because they are so close and our times are so close, that the rounding error has caused us to get a value that's a little below what it should be. So it wouldn't be wrong if you did answer this way. It also wouldn't necessarily be wrong if you said they were equal either, so just pay attention to rounding.